Good morning everybody. So today we will start on a different chapter, chemical admixtures. Again, this is presented in your textbook to a fair bit of detail in sections 8.1 to 8.4. We will also talk about some issues that may not be there in the textbook which are deriving more from the experience that we have had working with different types of chemical admixtures in our laboratory. Okay. So the purpose of this segment is to introduce you to the different types of construction chemicals that are typically used in concrete technology and look at what kind of interactions they have on a micron level, just to try and understand how well they can interact with the cementitious materials and what kind of properties are born out of that interaction. Okay. So of course you all know what chemical admixtures are. The term admixture, of course, you know, is not an English term, it is a concrete technology term, and it simply means anything that you add to the mixture, right, concrete mixture. So it is a chemical additive that is added to the concrete mixture and enhances the properties of concrete in the fresh or hardened state. So that is the simple definition of a construction chemical or a chemical admixture. But a larger family of construction chemicals also includes protective coatings and paints which are not covered within the chemical admixtures. So admixture is something which you add integrally to the concrete mixture during the time of mixing, right. So that distinction you need to make. If you look at the official ACI American Concrete Institute definition from Committee 116R, it says the term admixture is a material other than water, aggregates, hydraulic cement and fiber reinforcement which is used as an ingredient of concrete or mortar and added to the batch immediately or before or during its mixing. Okay. So either you add it before the mixing or during the mixing process of the concrete or mortar, and that is called an admixture. So what are the different types of chemical admixtures that are popularly used? We all know very well that the most popular type of chemical admixtures include water reducers. We will discuss this in a fair bit of detail, and we will also talk about set controlling chemicals which can affect the initial or final setting time of the concrete. We will talk about air entraining agents which are used very specifically for resistance to freezing and thawing. These three types are the more commonly used types all around the world, but apart from these there may be other specialty admixtures that are used in very specific circumstances. So we will talk about different types of specialty admixtures including viscosity modifiers, corrosion inhibitors, shrinkage reducing admixtures, SBR latexes and also some other minor types of specialty admixtures which have very specific purposes. They are not added to the concrete all the time, unlike the top three which are possibly used all over the world. Okay. So let us look at some aspects of water reducing chemicals. Now water reducers are further classified into two types. One is called normal water reducer and the other is a high range water reducer. The common terminology in the market for water reducers is plasticizer, and for high range water reducers it is superplasticizer, given the kind of performance you can actually expect from high range water reducers. Okay, so what does it mean? What does water reduction mean? Any idea? What is the meaning of water reduction? What water are you reducing? The water required for a certain workability in concrete can be reduced by the use of these chemicals, and as a result what happens? The strength and durability will go up because the water to cement ratio is reduced. Okay. Alternatively, you can keep the same water cement ratio, and when you add the superplasticizer you are going to increase the flowability of the concrete or workability of the concrete. So you can use these chemicals in different ways. So for a given workability the water demand can be reduced and that increases strength and durability. For a given water cement ratio and strength, if you simply add the plasticizer you increase the workability. So obviously that results in improvement in your construction methodology because you can actually now place your concrete at higher workability, so lesser energy input is actually required to compact and finish the concrete. Okay. But a third more important manner in which superplasticizers can help in concrete technology is that since you are reducing water, you can reduce also an equivalent amount of cement, okay, and achieve the same level of workability and strength that you were setting out to originally. What am I trying to say here? Let us say you have a concrete which you need to manufacture for grade M30, 30 megapascal grade, right. So for this what will be the approximate cement content that you use? Let us say we have a 30 MPa concrete. What cement content will you use typically? Yeah, in the field generally it is around 400 kilograms is used. What about water to cement ratio? if you have to do it without chemical admixtures and you want a slump of, let us say, 100 to 150 millimeters, what should be your water cement ratio? Around 0.5, yeah, 0.5. Okay, that means a water content of 200 kg per cubic meter. All right. So now let us say we add this superplasticizer. Typically these superplasticizers or plasticizers are added in terms of percentage by weight of the cement, okay, and generally the amount that is added varies between 0.5 and 1.5% by weight of the cement. Okay, I will come to that in more detail little bit later, but let us say we use at 1% by weight of cement. So superplasticizer, let us say we are using 1% by weight, that is 4 kilograms, right. I am not changing cement content, I want to keep the same cement content, okay. So what I am trying to do now is reduce my water by using up to 4 kilograms of superplasticizer. Now depending upon the type of chemical, the range of water that can be reduced can vary. So you come back to the top table, it tells you that for a normal water reducer, you can obtain up to 5 to 8% water reduction. For a high range water reducer, you can go 15 to 25% water reduction. So at 1% substitution, you can easily attain that 25% water reduction. So let us say we reduce 25% water. So new water content is how much? 25% reduction means 150, 150. So let us say I want to keep the same water cement ratio. So now cement content will be 300. So now I had two mixes, okay, assuming that we have the same slump requirement from both, let us say 100 to 150 millimeters at the time of placing. In the first mix I had 400 kilograms of cement and 200 kilograms of water, no admixtures. In the second mix I have 300 kilograms cement, 150 kilograms of water and 1% by weight of cement as the superplasticizer, okay. So what have I done essentially? My strength will be different. Will my strength be different? Maybe not, because my water cement ratio is still the same, okay. Maybe some aspect of the filler effect of cement may reduce, right, but then I do not know how much of an impact it will have on a strength which is already at the lower end. We are talking only about M30 concrete, okay. So now what I have done is I have reduced my cement content by 100 kilograms, I have reduced my water content by 50 kilograms. So what are the benefits? Obviously when I am reducing cement, the cost of this concrete is reducing, but you will say that I am adding a chemical, so isn't the cost increasing? So let us see if the cost is increasing or reducing. So the first case I have 400, second case I have 300. So cement savings is 100 kilograms. So approximate cost of cement is how much? 6 rupees per kilogram, yeah. So 600 rupees. 600 rupees is savings in cement. Now the admixture we have used 4 kilograms of, and most typically the kind of admixtures that provide this about 25% water reduction will be available to you nearly at about 40 rupees per kilogram, okay. So cost of admixture is 40 rupees into 4 kilograms, that is 160 rupees. Cement savings is 600 rupees, but the cost of the admixture is only 160 rupees. So economically you have made a sound decision by using the superplasticizer. Environmentally you have made a sound decision because you have reduced cement by 100, implying that your overall CO2 emissions that you expect from the concrete has also come down. In what way? Because cement production leads to a large proportion of CO2 emissions around the world. You must have seen the figures that 6 to 8% of CO2 emissions around the world are because of cement production. So if you reduce the quantity of cement used in concrete, you already give a very good picture environmentally, right. But another important environmental benefit is that you are using less amount of water for this concrete mixture. Now in today's world, you will increasingly realize when you actually go into practice that water is getting to be a very scarce commodity, especially water for concreting purposes. You know that it has got to be of a quality that is almost equal to drinking water. That level of water is not easily available today. So if you can come up with strategies to reduce the water impact in concrete, those will go a long way in helping us preserve the water resources for the future. So again, sustainability is easily achieved when you are talking about superplasticizers, because you are reducing cement, you are reducing water, okay, and you can say maintain the same level of concrete properties. Now, this does not mean that I can do this ad infinitum. For example, I can't reduce 400 to 200 just by the use of a chemical admixture. That may not be possible. When I am reducing my cement content by so much, I am totally going to be losing the filler effect. So, I may want to add some additional fillers which are of the same fineness as cement, and that may also incur some additional cost. But to some extent, this reduction in cement can be effectively done for concretes which are made with low grade. Now, many of you have had field experience. You must be seeing that even for low grade concrete, people are using 7 to 8 bags of cement for M20 concrete in the site. That is because they are not allowed the use of any admixture. So, they need enough water content in the concrete mixture to get workability. So, instead of water, if you have the option of using an admixture, you can then cut down your cement content, because effectively you can work with your concrete with lower water content. So, there is distinct benefits of using chemical admixtures. In the past, we used to think that chemical admixtures are only necessary for high grade concretes where we need very low water cement ratios. But today, I think increasingly, because of this third characteristic of the water reducers or superplasticizers, we should ensure that chemical admixtures are used in every concrete, not just high grade but also low grade concrete. Okay. Now, of course, this does not apply to volume batching. Okay. You know that a lot of concrete in our country is still produced by volume batching. In volume batching, there is no control on the extent of water that you are adding in the system. So, of course, as concrete technologists, we really have to ensure that there should not be any volume batching. We have to engage only in weigh batching to produce our concrete, because weigh batching can control the design of the concrete accurately and help us get the right amount of proportions of all the ingredients, including water. Okay. So, the days of 1:2, 1:3, 1:2, 1:4, that is in the past. We should not be looking at those at all. And in fact, today, very interestingly, I have also seen that many people have the habit of still putting proportions together after even a weigh batching based mix design has been done. So, people find out the weights in kilogram per cubic meter and then represent the weights in terms of proportions of cement to fine to coarse aggregate. That is not the correct practice, because it can easily be misinterpreted as a volume batching. So, you do not want to give that impression. So, as far as mix designs are concerned, we need to ensure that all our mix designs are specified in terms of kilogram per cubic meter of the ingredients and not in terms of proportions. Okay. So, moving forward, just to give you a very simplistic definition of what superplasticizers can do, this is a picture that has been reproduced from your textbook, Mehta and Montero. So, here you see that without the superplasticizer, the curve that is there to attain a given level of flow, that means a given level of workability with respect to the water content in the mix is presented. So, let us take any particular water content here, 200. Okay. Let us say I want to simply increase the flow here. So, what I am trying to do is simply moving up this axis. So, I am keeping the same water content and I am adding the superplasticizer, that leads to a shift in my flow or increase in my flow. Alternatively, I am still at 200 water content, I want to reduce my water to increase my strength and durability. So, I add the admixture, I maintain the same flow level, to obtain the concrete with lower water cement ratio. Okay. So, there are distinct benefits obviously of using superplasticizer, and that is simply conveyed by the help of this curve. Just to prove this point further, I will show you another picture later, but what are these water reducing chemicals? These chemicals are essentially organic polymers which are water soluble. Okay. So, water soluble polymers, most chemical admixtures that are used in concrete technology are water soluble polymers. So, normal water reducers, that means the ones which give you about 5 to 8%, maybe maximum up to 10% water reduction, are most commonly based on lignosulfonates. These are salts of sulfonated lignin, either sodium or calcium salts can be there. Okay, sodium or calcium salts of sulfonated lignin. Where is lignin obtained from? Wood. Yeah, lignin is obtained from wood. Right, wood has cellulose fibers which are embedded in a matrix of lignin. You extract your wood, lignin from wood. In what type of an industry will lignin be extracted? Paper manufacturing, right? Paper processing industry, you can actually extract the lignin and it undergoes sulfonation process that produces the formation of calcium or sodium lignosulfonate. Okay. That is an excellent water reducing chemical. The other common water reducing chemicals include hydroxy carboxylic acids like citric or gluconic acid. Okay. You can also use carbohydrates, corn syrup, dextrin, even sugar is a good water reducer. Normally these are used at a dosage of about 0.3 to 0.5% by weight of cement. You can't use too much because when you increase the dosage there is air entrainment in the system. Okay. You will see later that the type of chemicals that we are looking at as far as water reducers are concerned are similar to the class of chemicals called surfactants, like your detergents for instance. So, they are going to be increasing the extent of air that you entrain in the concrete mix. You can also have excessive retardation if you go too high in the dosage with these chemical admixtures. Again I will explain why that happens. So, you need to ensure that you keep the dosage fixed to between 0.3 and 0.5%, because beyond that effectiveness of these admixtures can reduce significantly. Okay. High range water reducers. So, what people started off with is trying to use the lignosulfonates at high dosages, but then they found that this was leading to high retardation and air entrainment, and because of that they were not very successful in using high range water reducers in the form of lignosulfonates. So, later the second generation admixtures came into being. These were polysulfonates. The most common one all around the world is the sulfonated naphthalene formaldehyde. Especially in India, that is a very good admixture because it works very well in the warm climate that most of India has, right. So, sulfonated naphthalene formaldehyde or sulfonated melamine formaldehyde. Again, these are polysulfonates. These are also called polysulfonates. These were the second generation admixtures that probably started coming or becoming popular in around 1970s. Okay. Those of you who are interested to track the history of how superplasticizers were developed or started getting used extensively in concrete also should look at the history of the rise of skyscrapers in the United States, and that is principally where people started developing these chemicals to ensure that they were able to work with higher and higher strengths of concrete. So, in the early 70s people were trying to come up with very high strength concretes. In those days very high strength meant over 40 megapascals. Okay, people were routinely working with 20, 30, and for them 40 was a difficult target to achieve because they had to reduce water significantly and could not increase cement to a large extent because that was producing all kinds of negative impacts like cracking, thermal issues and so on. So, because of that the research on chemical admixtures really picked up during that late 60s, early 70s period, and especially if you read the history you will see that many of the skyscrapers that came up in Chicago in the United States, that those were amongst the first ones to come up with very high strength concrete to be used in construction. Okay. So, anyway, so if you go through that in more detail, I am sure that there is several sources that will actually give you that information. But later towards the middle 1980s and late 1980s, in Japan there was a lot of work being done on self compacting concrete, and that led to the research on even more effective chemical admixtures, effective superplasticizers, that led to the development of the third generation, which includes mainly polycarboxylates. Today polycarboxylates are most commonly used, but you also have polyacrylates or monovinyl alcohols. So, these were the third generation admixtures. Today if you use these you can actually get up to 40% water reduction. You can get up to 40% water reduction. That means you can practically turn a zero slump concrete into a flowing concrete. That is the extent of impact that these superplasticizers can actually have. So, today most probably when you have a self compacting concrete you would be using a polycarboxylic ether based superplasticizer. Okay. Now, I will talk a little bit more about the structure of these plasticizers later, but again the chemicals that are used as superplasticizers are derived from other industries. So, lignosulfonates we talked about derived from the paper manufacturing. The polysulfonates and the polycarboxylates are coming off leather processing industries. So, there are several industries which actually have these chemicals that come out as byproducts in certain other processes. But now of course chemical admixture manufacturing has directly taken up the polymerization and production of these polymers directly by construction chemical industries. So, there are several large construction chemical industries around the world Can you give me some names? BASF is the most popular one. Phosroc, Sika. So these are construction chemical industries, probably these three, and of course Grace. So these 4 companies you will come across all over the world. Okay, they are present all over the world. If you have more local ones, in Chennai for instance, we have Serachem. You can also hear of something called Dawn Construction Chemicals. Yeah, so there are several construction chemical companies today. A few of them make the polymer on their own. Other companies actually purchase the polymer from manufacturers and then modify these formulations to produce their own admixtures. So not all the companies actually manufacture the polymers. Okay, only a few of them have a proper background to actually prepare these polymers. Okay, of course, there's other international companies also. There's MC Bauchemie. There is Wacker. I think Wacker also makes some construction chemicals, and Wacker makes a lot of waterproofing agents, and there's Mappe. So these are companies that you will come across in practice. You will find different kinds of compounds from these companies used in different websites, not websites, construction sites. We say websites so often these days that I've used that instead of construction site. So typically the dosage of these admixtures is at the rate of about 0.7 to 1%. Now that does not mean that you can't use above that. You will have to be careful when you use very high dosages, because again it is just like a drug, right? You are giving concrete a drug, and if you overdose the drug, you are going to cause problems. So in this case also, if you overdose chemical admixtures, you may end up with problems with the concrete. Most probably the problems are going to be dealing with excessive retardation, lack of early strength. Okay, I have heard people coming back from sites and telling me that concrete has not set for 3 days, 7 days, sometimes even 20 days. Okay, that is because they probably have used inadvertently a greater amount of chemical admixture in their concrete. So what do you think we should do if the concrete has been overdosed with admixture? What is the remedy? Can we remove the concrete from the place that has been cast? Probably not, difficult. What do you do then? Add an accelerator, but how will you disperse it in the concrete? You can heat the concrete, you can provide some external heating to speed up the reaction a bit, but in most cases you just have to wait, that is all, can't do anything else. You just need to wait, because application of external heat is not possible in all sites. So you just have to wait until the concrete sets and hardens. It will happen eventually. You won't completely lose the concrete, but it will probably take a little bit longer to set and harden. So let's look briefly at where these chemicals are derived from. I mean, this is not something that we look at a lot in terms of civil engineering, but just to get an understanding of where these are coming from. Lignosulfonates, as you rightly expect, are coming from the paper processing industry. So essentially the waste liquor obtained during production of paper making pulp from wood, that has a lot of lignin, and that is where we get this lignosulfonate. We get the lignin of course, and then there are reactions where you change the structure of the lignin by sulfonating it. Polynaphthalene formaldehyde condensates are produced from naphthalene by oleum or sulfate sulfonation, and what you do is react them subsequently with formaldehyde, and that leads to polymerization. You have heard in chemistry about condensation polymerization. When there are 2 different components, when they are added together, they start forming links and longer chains. And of course, there is in the end process you need to actually neutralize the chemical with either sodium hydroxide or calcium hydroxide. That leads to either a calcium bearing salt or a sodium bearing salt. I mean calcium bearing polymer or sodium bearing polymer. You can have sulfonated melamine formaldehyde that are manufactured by resinification of melamine formaldehyde condensates. And then polycarboxylates are a little bit more complex, but they end up producing polymers that can be suitably modified depending upon the kind of application that you are looking at. So today many construction chemical manufacturers actually come up with very interesting variants of polycarboxylates which can have other functionalities also. For example, some of these polycarboxylates can be modified in their structure to also be accelerating, some can be retarding, some can actually have an additional component of shrinkage reduction. So a lot of functionalities can actually be given to the kind of polymers that are produced for this polycarboxylic ether based admixtures. And that essentially happens because of course the polymer structure is something that you already know of. You understand that polymers can be having single monomeric units, or it can have a coupled monomeric unit that happens because of condensation essentially. So, you form these copolymers. In most cases all your chemical admixtures are copolymers, and in several cases what happens is there are counter ions present on the structure of the polymers itself that leads to some sort of a surface charge that these polymers can have, and this surface charge only leads to very interesting characteristics to some of the polymers. We will come back to that when we look at how these polymers are actually effective in providing water reduction in concrete. So, in terms of molecular structure, of course you are all experts in organic chemistry, so I do not have to explain this too much to you. So, essentially the molecular structure is defining the structure of the monomeric unit. So, in lignosulfonate you see that there are several benzene rings, and then you have the sulfonate group which is attached to the long chain here, and in terms of the molecular weight, the average molecular weight is about 20 to 30,000. So, the higher the molecular weight, the more the effectiveness of the admixture. Okay. In terms of the sulfonated naphthalene formaldehyde, you see that you have the basic naphthalene structure and you have the sulfonate attached to a certain position in the naphthalene structure. Okay. And sulfonated melamine formaldehyde again has this basic melamine unit and which has been sulfonated, and there is also formaldehyde attached in this chain which produces the monomeric unit. Now, the interesting part about this polycarboxylic ether is that you have this side chain that is extremely bulky. So, that means you have a main chain which is long. In all the other polymers you have a long chain structure of the polymer, but in the polycarboxylic ether and the third generation admixtures you have very bulky side chains coming from the long chain. Okay. So, bulky side chains are coming out from the long chain polymers, and this bulky side chain is what gives the new generation admixtures a slightly different mechanism of action. I will show you what that is. But before that, there are several methodologies which are applied to characterize the superplasticizers to try and understand their properties. Okay. There are several properties that are important as far as their effectiveness is concerned. The primary ones which civil engineers are most concerned with and quality control specialists in concrete manufacturing industries like RMC industries should essentially at least determine the percentage solids that are there in the admixture. Okay. Because the solid component of the admixtures are mostly sold as liquid formulations, you all know that well, and the solid component is the active ingredient in the admixture. The remaining part is water. Yeah. So, these solids are dispersed in water because they are water soluble, they are dispersed in water because that is an easy way of dispersing them within the concrete. If you put the solid material into concrete, dispersing becomes difficult. So, that is why most superplasticizers are sold in terms of liquid formulations. So, it is very important to understand what the solids content of the liquid is, because how do you determine solids content? Just take it to a temperature more than 105 degrees Celsius. In most cases that will drive off all the free water that is present and you will get the solid ingredient remaining. Okay. So, mostly that is what is done, and it can be easily done in a QC lab because you are routinely checking the moisture in the aggregate. So, you can also do the extent of liquid present in the admixture. Sometimes problem is when you heat to 105 degrees Celsius, some of the polymer structures may also get affected, which may change the solid content. So, there may be some other methodologies by which you can actually determine solids content, but that is most important as far as superplasticizer effectiveness is concerned. So, when a new batch of SP comes, you need to ensure that the solids content is maintained at the same level, otherwise you will get a major distinction in the performance. So, QC labs on site should do solids content determination for chemical admixtures. Anyway, there are several other things which we do not do all the time as far as civil engineering is concerned, but the chemical admixture manufacturers use several different methodologies to actually characterize the type of superplasticizers and their interactions with the cement. So, when a superplasticizer is produced, it is not only the chemical structure that is important, how the structure actually interacts with the cement, that is also a very important characteristic that needs to be addressed carefully. Okay. So, what is this dispersion effect? You know very well that when you have a low workability, for example, here it is shown in the case of a paste, right, addition of 10% water is increasing that workability significantly and you get a larger spread. But instead of that additional 10% water, if you simply add a small amount of this polynaphthalene sulfonate, you end up getting the same sort of workability as you would have got with additional water. So that tells you the dispersion effect of the plasticizer. So what is happening in this system? Why is dispersion happening? So what is responsible for providing workability in the concrete? What is responsible? Which ingredient of concrete provides workability? Cement paste, but within cement paste? Water, right? The more water you have, the more workable your concrete will be, of course, until the point of segregation, right? So water is the one which provides workability. Now what happens here? You also have water here. Why is this water not providing workability? It may be not sufficient, or it may be not able to move around freely to provide a flow characteristic to the paste. What do you do to make it move around freely? You need to free up the cement particles, separate the individual cement grains so that the water can move between them freely to cause a dispersion of your cement paste. Okay? So that is essentially what a superplasticizer does. The old type of superplasticizers like lignosulfonates, the polynaphthalene sulfonates and so on, what these end up doing is the polymer chain. So supposing you have your cement particle like this, the polymer chain wraps itself around the cement particle by adsorption. Okay? And what it does is, after surface adsorption, it lowers what is called the zeta potential. Now what is the zeta potential? When we produce cement, we do grinding in the final stages of cement manufacture. When you do grinding, you leave the material with some surface charge. Okay? Certain particles of cement may have a positive charge, certain types may have a negative charge. So what these superplasticizer molecules do, the naphthalene sulfonates or lignosulfonates, is that they go and wrap themselves around the cement particles and end up providing a like charge to all the cement particles, negative charge. Okay? They provide a like charge to all the cement particles, and of course you know from electrostatic principles that like charges will repel. So cement particles end up repelling each other and spread out into the paste. So what happens originally, without the superplasticizer, you have these cement grains which end up forming what we call as flocks. This is common to all fine powders that will be in suspension in water, that they will tend to agglomerate and form flocks, because again they have surface charges here. Okay? So the flocks will trap the water inside and prevent it from moving around freely, which causes workability. So what the adsorption does is that it creates like charges, causes the cement particles to repel each other and causes the water inside to get freed to mingle outside or to flow freely outside. That leads to workability of the paste. Okay? So that is the mechanism of action of substances which have functional groups like lignosulfonates, polynaphthalene sulfonates or sugar refined lignosulfonates. So lowering, so first process is surface adsorption. Second is lowering of zeta potential, that means the charge on the surface becomes more and more negative. Okay? So lowering of zeta potential. And the third process is electrostatic repulsion. So you have surface adsorption, lowering of zeta potential, and finally electrostatic repulsion that happens in the case of conventional water reducers or conventional superplasticizers. So again this is the same depiction. You have the cement grain here which is shown to have a positive charge. Some grains of cement may have positive charge. For example, the aluminates and so on, those are known to have a positive charge, whereas the silicates may have a negative charge. Okay, so again these are the polymer chains that are getting adsorbed on the cement particle, and the polymer chains which have the anionic polar group end up giving the negative charge to the cement particles. Okay. So essentially the polar chain is adsorbed alongside the cement particle. Instead of directing non-polar end towards water, in this case the surfactant directs a polar end. So these are all surfactant chemicals which are directing the polar end towards water, reduces surface tension. Okay. That means the water becomes more easily flowable, okay, and the cement particles become hydrophilic as a result of this polar chain getting oriented towards water. So, surface adsorption leads to negative charges on the surfaces of fine powders. Generally, the higher the molecular weight of the chemical, the higher will be the surface adsorption. And generally, if you have calcium bearing salts instead of sodium bearing salts, you get better surface adsorption on the cement particles. Okay, so again, as an admixture, you are just getting the admixture, you do not know whether it has got a calcium salt or a sodium salt. But sometimes when the source of the admixture changes, if your performance is changing, one of the reasons could be that you have switched over to a different chemical which may be a sodium salt or a calcium salt. You understand? So, as an engineer, you do not necessarily have to tell the construction chemical manufacturers how to formulate their products, they know that well. But when you get a problem in your concrete as a result of the application of the admixture, you should have an idea what may be the cause of this problem and try to identify this cause with the help of the chemical manufacturer to try and work out the best strategy for your job site. Okay. So, the electrostatic repulsion, if you take the example of sulfonated naphthalene formaldehyde SNF, this is effective for both positively and negatively charged particles. I told you that cement grains can get different charges because of the grinding. So, SNF effectively adsorbs on both positive and negative charged particles. And if you have more and more charge on the polymer, then the effectiveness increases. In other words, if you have SNF with a fairly high molecular weight, that means there are more links in the chain, so there will be greater charge on the surface of the polymer. So, that will increase the effectiveness with which it provides the electrostatic repulsion. And it is interesting that when you actually come back to the structure of this polymer, this sulfonated naphthalene formaldehyde structure, the sulfonate group, if it is present in a particular location, which of course in organic chemistry you know that there are different parts of the benzene ring which are given a different notation. So, if it is present at the beta position on the naphthalene ring, or naphthalene is a combination of two benzene rings. So, on naphthalene, if it is present in one of the positions called beta position, it leads to a higher degree of effectiveness in the superplasticizer. So, this is a strategy used by construction chemical manufacturers to come up with more effective chemicals to ensure that the dispersion they produce in cement paste is optimal. Now, the problem is when you are adsorbing the chemical on the cement particle, there is a possibility that you may also block some reactive sites and prevent the reaction of cement from happening fast enough, right. So, some low molecular weight organic materials are responsible for doing that. They cover the reactive sites and inhibit the reactions. These low molecular weight ingredients which may be present in your admixture include starch and glucose, sugars essentially. Okay. What will happen as a result of this? If you are going to be inhibiting reactions, the setting time will go up or retardation will happen. Okay. With sulfonated naphthalene formaldehyde, your reactive sites may be inhibited by low molecular weight fractions like dimers and trimers. Dimers means polymers with 2 units, okay, 2 monomeric units, and trimers is 3 units. So, these are small chain length polymers. So, they may go and block the sites on the cement grain that are reactive and inhibit the chemical reactions, that is going to lead to retardation. So, what you need to do is modify your process in such a way that you can remove the low molecular weight materials. How do you remove low molecular weight materials? So, you want to reduce the low molecular weight materials which are going to be causing retardation, and this can be done by centrifuging. You know that centrifuging is a process by in which you spin the material at a very high speed, and when you spin it, what will happen? The higher mass materials will come to one side and the lower mass materials will go to the other side. So, in this way you can actually extract the ones which have a longer chain length and use those more effectively for providing the best kind of dispersion without causing this inhibition that actually happens with SNF. The starch and glucose is mainly from lignosulfonate. So, sugars can be found in tree extract also. So, there will be some starch and glucose present in lignosulfonates which may lead to this kind of a problem. Okay. And you will find later that this very aspect of lignosulfonates and of carbohydrates leads to them being quite effective as retarders also. Okay. So, as retarders, the same family of natural or normal water reducers that we saw earlier, those will also be acting as retarders in concrete. What about the polycarboxylic ether? I said that you are actually introducing a very interesting sort of a structure here with very bulky side chains. So, again you have surface adsorption. So, the polymer molecules, the long chain polymer molecules attach themselves to the surface of the cement, thus orienting their bulky side chain outward. So, look at the side chain, it is very bulky and it is getting oriented outward. Similarly, this is a neighboring cement particle on which you have, on surface of which you have this polymer adsorption, and then you have the bulky side chain orienting outwards. So, what is happening now is after you have the adsorption taking place, the structure of the polymer itself prevents the cement grains from getting together. Okay. In other words, flocculation is prevented by the bulkiness of the side chain of the chemical admixture, and this process is called steric hindrance. Okay. So, in the older generation admixtures, the repulsion was being caused because of charge. In this case, the repulsion is being caused because of steric hindrance. That is the difference between the old and new generation. Now, the problem with the old generation is the charge will diminish after some time. So, the effectiveness of the older generation admixtures in maintaining the slump would be low, whereas the new generation admixtures tend to maintain slump for a longer time because they do not depend on surface charge, they depend on the availability of bulky side chains in the material. Okay. So, the hydrates basically will start filling up the structure and then your charge will go down. When water starts reacting with the cement, your charge will diminish. But here the effectiveness of the chemical will last for a longer time because you are not relying on that charge. Okay. So, these are essentially the kind of chemicals that will have this type of an action, polycarboxylic ether, which is the most common new generation admixture used today. Okay. You can have cross-linked acrylic polymers or carboxylic acid with acrylic ester. So, these chemicals can actually provide you up to 40% water reduction and fairly good slump retention. Okay, you all know about the world record for concrete pumping for self-compacting concrete, that was with which building? Burj Khalifa, 600 meters vertically upwards, and you can imagine that the time taken for pumping the concrete up and then applying the concrete on site in a self-compacting form would have been tremendously large, and the slump had to be maintained for a long period of time, and that was done effectively by the use of polycarboxylic ether based superplasticizer. So, polycarboxylic ether admixtures or PCE admixtures act by steric hindrance, because of which they are effective at low water cement ratios, especially when you want to produce very high grades of concrete or ultra high strength concrete. You have to rely on polycarboxylic ether admixtures, and generally they are not known to have compatibility problems. With sulfonated naphthalene formaldehyde, if you are providing a very high molecular weight chemical, you may still get some steric hindrance, but it is secondary. The primary aspect there is the electrostatic repulsion and not the steric hindrance. Steric means related to the structure. Steric is related to the structure. So, structure, the polymer itself is bulky, that causes it to be more effective. Now, what people have ended up doing is, because they can play around now with this main chain and side chain of the PCEs, they have tried to impart a combination of different types of characteristics. So, for example, if you are in a precast application, you want very high flowability in the beginning, but your slump retention may not be large. You do not want a very large slump retention, you want, because your concreting gets done very fast. So, your slump retention there may be half an hour to 1 hour at the max. On the other hand, in a ready mix concrete application, you may not want very high initial workability, but you want to maintain that for a very long period of time. So, the initial workability is obtained by your surface adsorption. Okay. So, that means the longer length, longer chains. So, if you have low dispersibility and short dispersibility retention, you will be ending up with the backbone polymer which is long, the side chain length is short, and a large number of side chains will be provided to have a low dispersibility and short dispersibility retention. On the other hand, when you want high initial workability, you go with short background polymer, long relative side chain length and small number of side chains. If you want to maintain the same slump for a longer period of time, you may still go with shorter backbone length, longer relative side chain length and a large number of side chains to ensure that the polymer does not lose its effectiveness fast enough. Okay. So, this process can be controlled to a large extent by the construction chemical manufacturers to provide formulations that are attuned to a particular job. So, if you have a precast application versus ready mix application or a long haul application, you can actually alter the structure of your chemical suitably to give you the desired characteristic. Now, very quickly we will go through some types and properties of superplasticizers. We will talk later about what kind of interaction they may have with the cement and what drives those interactions. So, we will talk first about unrefined lignosulfonates, then melamine formaldehyde, naphthalene, and finally the new generation chemicals. So, unrefined lignosulfonates, we know that they are born from the first generation chemicals, and because of that when you use them at high dosages there is a wide variation in properties. You do not get effectiveness all the time. You may enter in air and get inconsistent performance primarily because of retardation that is caused by the high dosages of lignosulfonates because of sugars that are present inside the lignosulfonate. Generally these are large molecular weight. What you can do with this, because you know very well that sugar is causing retardation, you can try and do something which will remove the sugar, okay. And to ensure that you always get consistently good performance, you want to also keep the polymer chains long enough. That means you want to reduce the smaller chain lengths. So, what you do is you can do fermentation to remove the sugars. So, you ferment the sugars away to retain the basic polymer structure, but without any sugar, and the smaller molecular weight components that are leading to air entrainment because they are acting as surfactants can be removed by centrifuging, okay, and that may end up giving you modified lignosulfonates which are quite well used as superplasticizers. And the advantage with these is they are suitable for blending with sulfonated naphthalene formaldehyde and PCE admixtures. Now, one of the problems that we encounter, which I will talk about later, is that when you use SNF or PCE, you may get a very quick loss of slump, especially in very warm climates, okay. To induce some retardation into it, it is usually beneficial. The construction chemical companies typically add some lignosulfonates to prolong the setting time in warm climates. So, you should have chemicals that are miscible, only then this can be actually obtained. So, lignosulfonates are quite nicely miscible with both SNF and PCE based chemicals. So, essentially you are producing a concoction of different types of ingredients trying to get the desired characteristic for a particular application. Melamine formaldehyde in India, you will probably not find it used anywhere except in certain precast industries because it has got absolutely no slump retention in the warm climates. It is suitable only for cold weather and for precast concrete, especially when you have RMC and long hauls, you may not be wanting to work with melamine. The costs, especially what you find in India, could be highly unfavorable in terms of usage in concrete to a large extent. But naphthalene formaldehyde on the other hand, even in warm conditions it works quite well in terms of good slump retention. It can be blended with lignosulfonate to increase the setting time, and the cost is also quite favorable. Typically you will find that these are available at about 30 to 50 rupees per kg. Okay. Lignosulfonates will be much cheaper, but generally you will find that SNF is available probably at around 30 to 50 rupees per kg. Downside is you can't mix them with PC admixtures. Why do you want to keep mixing admixtures? Because PC admixtures are expensive. You want to bring down that cost a little bit. You want to put something cheaper inside which can still be effective. Unfortunately, with SNF and PCE there is no compatibility. Main issue with SNF is the problem in concrete with low water to cement ratios. We often call that as incompatibility, and we will talk about that in more detail little bit later. And finally, PCE based or those plasticizers that are based on these graft chain copolymers, they work quite well in low water cement ratio systems. They have good slump retention, they may not have any compatibility issues, and again dilution with lignosulfonate is possible, but not with naphthalene formaldehyde. Okay. These are expensive. Of course, the experience is no longer limited. People have been using these for nearly 20 years now, and especially in the last 10 years the usage has gone up by leaps and bounds. Okay. All right. So, again we will come back to